Welcome, everyone. I am Pasquale Bosso, and I am a member of the outreach activity team of the International Society for Quantum Gravity. Today, I will have the great pleasure of interviewing Professor Cliff Burgess. Thank you for having accepted our invitation for the interview, first of all. Professor Burgess.
Thank you for the invitation.
Professor Burgess is currently a professor at the McMaster University in Hamilton, Ontario, Canada, and also an associate faculty member at the Perimeter Institute for Theoretical Physics in Waterloo, also in Ontario, Canada. However, so probably it's better to hear your story, your academic story, directly from your mouth at this point.
I guess I grew up in Canada and did the usual high school thing. Went to the university actually in Waterloo, as it turns out, at the University of Waterloo, and then was a graduate student in the US. I went to the University of Texas, and then on graduation, I was a postdoc at the Institute for Advanced Study in Princeton. And I was very lucky in the sense that I got a faculty position basically in the first fall of my first postdoc at McGill University of Montreal, and I was there for 17 years before coming here to McMaster and Perimeter.
Oh, okay. So it's a very interesting career, a very rapid career also. So did you stay mostly in Canada and US, or did you move also to some other countries, some other continents?
I mean, as a child?
Also during your career, yeah.
Well, but so during my career, I was in those places. So I was in the U.S. for, I guess, 7 years, and then Canada since then, living. But then every sabbatical we did one sabbatical in Princeton, and then I guess we've done now 4 sabbaticals in Switzerland.
Oh, okay.
And when I was young, we moved around a lot. So we lived all over Canada, but also lived in Germany for 3 years and in the UK for half a year. And so kind of a smattering of countries.
So you traveled a lot, which is kind of a constant in our field. So traveling quite.
Yes, it's one of the pleasures of the field, I think.
Yeah, I guess so. I guess so.
Yeah.
Awesome. And so first of all, at this point, the question would be: so of course you're working on quantum gravity, and you're doing some phenomenology as well. And so, how did you get interested in this field, first of all?
Well, probably like everybody, quantum gravity is one of those problems that's out there as a big question, as is what is dark matter, and it's one of the big ones of our time. So I've probably known about it since I was a kid, but I actually trained as a particle physicist, and so I would probably have said when I graduated that I was not doing quantum gravity. But when I graduated I got my PhD in 1985, and in 1984, string theory burst on the scene in a way. So string theory had been around since the late 60s, but it really kind of burst on the scene as being something where a significant number of physicists that had not been doing it all their lives became persuaded that it had something to do with quantum gravity. And I was kind of lucky enough to be a student. In the last years of my PhD, all the professionals around me, like Weinberg and Polchinski, they were learning string theory because they had come to realize that it had something to do, it could have something to say about quantum gravity. And so it gave me a chance to learn it with them and also see how they learned it, which was also interesting. And I didn't immediately start working in it. My postdoc was in Princeton, and they were all doing string theory then. And so I did do some then because it was the perfect place to do it. In those days, when you're learning a field, you don't know the difference between what you don't know and what nobody knows. But by being in those places, you kind of had a sense as to what nobody knew because all the experts were there. So it was a great place to learn. And but I kind of just consciously left string theory and quantum gravity in the early 80s because I didn't think it was going to make any headway. Because in the end of the day, it seemed impossible to test experimentally. And in those days, the LEP accelerator was going to turn on, and there seemed to be much more to be done in particle physics. So I consciously steered towards particle physics for, in the end of the day, something like 20 years. But all of the interesting questions in particle physics ended up hinging on gravity. So all of the various naturalness questions about the hierarchy problem or the cosmological constant problem, or all the clues about what was missing in the standard model seem to be coming from gravity-related questions. And the experiments in places like the Large Hadron Collider, or in those days we didn't have a Large Hadron Collider, but the large at LEP hadn't found any problems with the standard model. In the 90s, neutrino masses were found, so you knew that there's some things wrong. And it was also true that the big tests of the microwave background, the satellite experiments like WMAP, were going to start, and so it seemed a good time to start thinking about the interface between particle physics and gravity, and particularly the things that would have something to say about the microwave background and primordial fluctuations. And the best pictures in those days involved explaining what we see in the sky in terms of quantum fluctuations that were generated in a much earlier time in the universe. And so that really required you to understand quantum gravity at some level, and in a quantitative way, because if you were going to ask anybody to measure anything, part of the story on the theoretical side was to have control of your theoretical errors, and to say that what you should be seeing is this, and the errors are that, and those errors include quantum errors because the thing you say you're calculating are quantum effects. And so it seemed important to understand quantitatively what controls quantum effects in gravity. And that kind of led me along the line of effective field theories, and it turned and just thinking of gravity, but in a there are many problems of quantum gravity that are interesting. Some of them are very high energy problems and are very fundamental, like where does space-time come from, and is space-time emergent, and all those kind of questions are fundamental, but hard to experimentally probe because they involve very small scales. But there are also practical questions about quantum gravity, such as an inflation, where quantum effects are being claimed to have been measured. And so then those are still quantum gravity questions, but of a different character, perhaps less fundamental, but also more practical. And so that drove me towards thinking about quantum gravity about 20 years ago.
Okay, that's very interesting, and actually, thank you for sharing this thought process. Let's say because it's always very interesting, how different people found themselves working in quantum gravity, starting from very different backgrounds sometimes. So
yes.
And do you want to tell us a little bit about your specifically what you are working on in this period, so in quantum gravity?
I guess so the theme for my research would be probably effective field theories. Even without quantum gravity, that would be what organizes the way I think about physics. But I think it's also true that describes the way I'm thinking about quantum gravity. And if for, depending what your audience knows about effective field theories, but effective field theories are essentially a tool for exploiting hierarchies of scale. If you have, nature comes with hierarchies of scale, and so ratios of scales can be small numbers, and generally things simplify when you can expand in those small numbers and you can get good approximations. And the point of effective field theories is the earlier in the calculational process you do that expansion, the better you profit from the simplicity of the answer. And it turns out that you can do that rather than calculating the answers and then expanding them to see what they look like at low energies. It's very efficient to calculate, do the expansion very early and then calculate the observables later, because it turns out that the effects of very short wavelength physics or very high energy physics can be captured in the Hamiltonian. And so once and for all, you can describe all of the influence of high energy effects on any observable you like if you can characterize this Hamiltonian. And that kind of sounds like it's a very specific tool, which works if you have a hierarchy, and so it seems like you could have the choice of using it or not using it if you're doing quantum gravity. But it turns out that there's always a hierarchy. You might think you wouldn't use it if you didn't have a hierarchy of scales. Maybe you're interested in inflationary scales and where all the wavelengths are the same size as the curvature, and you might say, well, I've only got one scale in that problem. But it turns out that in quantum field theory, there's always another scale that is playing a role, because short distance physics through virtual effects is contributing to everything. And the way we and that traditionally has been one of the problems of quantum gravity, is that the short distance effects show up in predictions in a way which seems like they could not have been renormalized the way that we we handle them in other interactions. And our modern understanding of how that works and why we're able to make predictions really relies on the fact, relies on effective field theories. It relies on the fact that that what you're essentially addressing there when you ask how short distance physics appears in ordinary calculations in quantum gravity involves implicitly a hierarchy of scales, because there's a hierarchy between what you're looking at and the scales that were short that were the problem. And once you organize your thinking that way, then it's possible to really make quantitative predictions in quantum gravity, but you can only do it at low energies compared to the Planck mass, say, because you're building into it the whole story of a low energy limit, and eventually something has to replace that at higher energies, and perhaps that's string theory. And what's nice about string theory, I have no axe to grind about string theory, but what I like about string theory is that it's very precise, and so you can ask very precise questions. Even if nature doesn't work that way, at least that's an example of a theory that could be the fundamental theory, and you can ask how it would change things at low energies.
So actually, this is a good point. So basically, you are doing, well, as you said, effective field theory, but you wouldn't claim it to be a fundamental theory in the sense, so it's a tool to describe low energy, well, to have a low energy description of some other theory that can be string theory, for example. But it's a low energy description, sort of. Yeah. Right.
And I think that makes it sound like it changes the way you think about what you're doing when you write down a theory. You're no longer, writing down what God's thought. It's more like you're writing down a laundry list of what was going on at very low energies of what God thought. But I think it's true that's the only, when you think of things that way, it explains why the classical approximation is a good approximation, because it turns out that the expansion you're doing when you think of gravity classically is an expansion in the derivatives. If you ask the size of quantum corrections to any classical prediction, it's controlled by the ratio of the energy scale of interest to you and essentially the Planck mass, typically squared. And because that's why it's incredibly small in the solar system. But the fact that you can quantify it comes because you can actually compute what the quantum effects are in a controlled way. And so what that means is that anybody who's making, what people typically do or often do in quantum gravity, often in cosmology in particular, is the quantum part's not playing an important role. People will make up a theory of gravity, they'll modify it some way, and then they'll extract its classical predictions. And they often don't tell you what controls the classical approximation. And that's a mistake, I think, because particularly if you're interested in inflation, where you think that quantum effects actually have been seen, then it's clear that the quantum effects aren't negligible. And so then you have to understand, how big are they and why don't they include everything? And so everybody in practice, I think, who are in cosmology at least, who are thinking about making predictions and if they're quantifying their errors and quantifying how big their quantum effects are, the only known way to do that, I think, is it through effective field theory. So I think in practice, everybody's doing effective field theory, even if they don't admit it. So I think it's a very, very powerful technique that is, there's no doubt that it's a good way to think about, efficient way to think about low energy physics. You may ask questions which don't involve low energy physics, like maybe in string theory, you want to know the whole string answer, but there's very, very rare, in practice, when you're comparing to observations, it's almost never true that effective field theory is not useful. So it's a very powerful tool to have.
Yeah. No, I mean, yeah. And of course, since we live, compared to the quantum gravity energy scale, we live in the low energy regime. So at least we can, compare their predictions from effective field theory with what we see. So. Yeah.
But what I haven't answered your question because that's the framework I work in, but I could have actually told you that framework as a graduate student, because more or less this framework was invented by Weinberg. And I remember taking quantum field theory from him, and he made it sound like everybody knew this. and it turns out that actually that picture is kind of spread out through physics, particle physics and other areas too, starting from him. But as a graduate student, it would have been worth knowing that people that you had inside information that other people didn't have, because it would have suggested things to do. But so the actual research program now is not so much it uses effective field theories, but what's interesting to me now is there are some senses in which the things that you see in gravity are different kinds of effective field theories than we see in particle physics typically.
Okay.
And so that's interesting in itself, independent of the gravity. Gravity is kind of a tool for learning about how the theories work in this kind of slightly different situation. And let me give you a concrete example of that. So one of the things that the way I kind of one sense in which effective theories are different for gravity is if you have a horizon, for example. In a traditional effective theory, what happens is that you're looking at low energy degrees of freedom and you're not looking at high energy degrees of freedom. So you're kind of identifying a subset of the degrees of freedom that you think is important. But when you have a horizon, a similar thing happens where things go through the horizon and you can't see them. So you might be describing things on what's on your side of the horizon. But there's an important difference between a horizon, let's say, and a normal traditional effective theory, because in a traditional effective theory, what separates what you see from what you don't see is a conservation law, basically energy, that you're distinguishing the things you're choosing to look at by their eigenvalues of some conserved thing like energy. And because of that, if you start off just at low energies, then conservation of energy says you'll stay at low energies. So there's always a Hamiltonian description of it. It's just a question of what that Hamiltonian is. And so the whole story normally for effective theories is finding out what the Hamiltonian is. And one of the interesting things is it tends to be local. And that's because of the uncertainty principle. The things you're not looking at are very high frequency or very short wavelength. And so they can't influence things because of the uncertainty principle over scales that are very large in distance or in time. And so then that leads you to why you're thinking about local Hamiltonians. But in a case of a horizon, you don't have that argument. So that when you describe what's on one side of a horizon, it's much more of an open quantum system picture where there's just some stuff you're choosing not to look at, but there's nothing special about it. Things that have the same energy of you could have fallen through the horizon and you can't see them. Mm-hmm. And so because they're not separated from you by a conservation law, that they can do things that you don't normally see in effective theories. Like you get things like thermalization, or you get things like decoherence that can happen. And so that kind of physics is something which, as a particle physicist, you're not trained in those tools. And so the open quantum system tools have been a very how you interface open quantum systems with effective field theories has been a thing that has been of interest to me, because things like opality that we take for granted might break down.
Yeah, and so you mentioned open systems, which sometimes, for example, is approached in solid state context, right? So can you clarify? So how can you use concept from, for example, condensed matter and solid state into quantum?
Yeah, definitely, and that's actually, I think it's a really fascinating thing. So open, a classic example of an open system might be that if you have if condensed matter people use this, but also optics people use this. If you have, say, light moving through a glass or something, then you're choosing normally to see what the light does, and you don't care what the glass is doing so much. Mm-hmm. And so in that sense, your system was both of them, but you're choosing to do measurements only in some subset of your system, in this case, the light, and not measure the glass. And so the way you set that up is given that you're doing only measurements in a subset of your system, then you can trace over the degrees of freedom that you're not interested in, and you can set up in a very general way what they call a reduced evolution, which describes the evolution of just the system that you're measuring, but it includes the influence of the stuff you're not measuring in a systematic way. And you can, for example, you could work perturbatively in the strength of the interaction between your system and what you're not looking at. And for a particle physicist, there's a lot of surprises there that I think for condensed matter physicists and for optics people is not a surprise. One of the surprises is that as soon as you do things perturbatively like that, it's always true at late times that perturbation theory fails. And there's kind of a really simple reason for that, but it's in particle physics, we're not used to the idea that at late times perturbation theory fails, because in particle physics, we often ask scattering questions where you have some wave packet, it overlaps with another wave packet, and then they separate, but they only interacted for some small amount of time, and they didn't interact for a long time.
Yeah, we don't know where they come from and where they go.
Right, right, exactly. So late times don't exist for us, but if you have a medium like glass, it just sits there, and if you're in it for a long time, then even very small interactions can accumulate over time, and they can start to ruin things. And the classic example of that would be refraction and reflection. If you think of the interactions of any one photon with any one atom, they're very weak because the electromagnetic interactions are weak. And you might have thought that, well, so that means that any optical properties of matter, I should think of them as being suppressed by the electromagnetic fine structure constant, and they should all be very small effects. But what you know is that if I send some light into glass, then after some time, essentially everybody refracts or reflects, and that's it. Nobody goes straight through. Nobody. So that's by almost by construction. That's the best example of or it's a good example of a place where perturbation theory breaks down, because perturbation theory says more or less nothing happens, and there's small changes to that, and that's not what happened. Is that nobody's going the way that the original beam went. They're all going in two different directions, and that's because what happens is that although any interaction with one atom is weak, once you go by 80 billion atoms, then it's not weak anymore. And so then everybody kind of coherently goes down and up. And so understanding that kind of shows you that there's a generic problem with perturbation theory at late times, but it also shows you that you can still say things at late times. You don't have to solve quantum electrodynamics exactly to say things at late times. We know a lot about optics, and so there's tools that allow you to resum late time behavior in a systematic way, even if you only have access to perturbative information. And those tools are, it turns out, I didn't realize this when I started. I kind of came into thinking about open quantum systems because I was thinking about horizons, but it turns out that these open quantum systems are also the things that provide you these tools for looking at late time behavior. And so, and resumming late time behavior. And so one of the research areas I'm interested in is taking these tools that have been developed in optics and in condensed matter physics, like how do you evolve the density matrix describing the system of interest to you at late times when you are subject to a weak interaction with an environment. And in the gravity case, the only difference is instead of the environment being glass, the environment is the gravitational field. So you've got some sort of a particle moving through a gravitational field and it just sits there. And so say it's a black hole or something, then you know that there are quantum effects, like things like Hawking radiation, but you know that if you wait long enough, those quantum effects can do dramatic things, such as make the hole evaporate. And there's a lot of puzzles that are associated with late time behavior. And I think that in those puzzles, too few of us are taking these tools that have been developed in a very well-tested area of physics and applying them in this new area where the people that are thinking about these gravity problems are typically not trained in these tools. And that's an opportunity. In our situation now in gravity and in particle physics is that it's a very mature field. People have been thinking about it for 100 years. It's almost never that you come across an area where there are new tools that haven't been used already by people in the 1930s. So I see quantum gravity as an opportunity in that way, that it's accessing tools that we haven't really used very much until now.
Okay, yeah, that's very interesting. And again, this shows one more time, how sometimes idea coming from different fields can help you do some work or some tasks that before you didn't realize it was possible. So that's actually
very much so. Yes.
Yeah. And also you mentioned cosmology. You mentioned inflation. So you work also in this field. So can you tell us something about that?
Yes, so I kind of probably do a little bit less in inflation than I used to, but so I started working on inflation. I had a sabbatical in the year 2000, 2001, and so I thought, and this was just before WMAP was going to start, so I thought I really should learn more cosmology because I think there's going to be a lot of interesting things to say in cosmology, and I had just been thinking about string theory, and it seemed like. It was clear at that time that inflation had very promising things to say about initial conditions, but it also seemed true that the energy scales associated with inflation are very high compared to the ordinary ones of particle physics typically, but they're not so high. They're not at the Planck scale. They're not so high that quantum effects are out of. There's no control over them, but they're kind of close-ish to the Planck scale, and that's kind of why quantum effects can be non-negligible. And but if you're close to the Planck scale, then it seemed like if you can actually have observable consequences from physics close to the Planck scale, then you're probably going to need a theory that works close to the Planck scale. And the only one that I could think of that was precise enough to ask the questions in was string theory. So then it seemed natural to try and ask, well, can you find inflation in string theory? And if you can, then hopefully what you could do is you could use that as a way to probe string theory on the one side, but you could also see if string theory has any particular insights into the kinds of inflationary models you might be looking at once you see the pattern in the sky more carefully and test it better. And so that's kind of was, and I wasn't the only person to have that thought. so many of us started to think about how can you get inflation in string theory, and that in the end of the day comes down to you have a bunch of things, objects in your theory, and in string theory that could be the strings. It could be, there's more than just strings in string theory. There are things called branes that the strings end on, and they are kind of much more big and massive, and they move more slowly. And so you kind of ask, in various situations as these things are moving, if I looked at the low energy limit of that, would that look like an inflationary world? And it turned out to be harder to do than everybody expected, in the sense that, and it kind of in retrospect, it was probably should have been more clear that it was going to be hard, because the key thing about inflation is that you try and have the energy of the universe that's gravitating to be hung up in some positive potential energy for a long period of time, and that's what makes the universe expand so dramatically. And that means you need basically a potential for your degrees of freedom, which is very flat, because you're not moving, or it has to have a minimum, and you have to be stuck there for a while. And the minimum thing was the first thing people tried, and the problem with minima is that it's very difficult to get out of them. And the trick is, what's hard about inflation is ending it. You know, once you get into inflation, you'd like to just stay there. And so the thing that worked the best, what people already knew by the late 90s, was that if you had a very, very flat potential, that was the kind of thing that seemed to be the simplest thing to work in inflation.
Low roll paradigm.
Right, exactly. And so the question was, can you get that in string theory? And the reason it's hard is that in string theory, you have normally many fields. So there's not just the one for the inflation, you've got a lot of fields. And the hard part was, you need to know the potential for all of the fields. It's not enough to know that there's some direction in field space which is very shallow, because if a different direction is very steep, then you're going to go the steep way. You don't care about the shallow way. Right. So the hard part was you had to actually find all of the potential as a function of all the directions, and show that the steepest one available was shallow. and that turned out to be tricky, and it involved being able to calculate more explicitly what these potentials were. And there was a big revolution that happened in the late 90s, where Polchinski and Giddings and Kachru and a few others developed tools for a class of string constructions to calculate this potential. And then you could really, the various proposals that we had made beforehand as to how inflation might happen, such as a brane and an anti-brane falling towards one another, those kind of things, you could actually really pin them down and test them more accurately, because you could really calculate all the degrees, everything was, what the potential was for all of the fields. And so in the 2000s, that was kind of a very active area of research, where people were trying to find if you can get inflation, and if you can, do you get kind of all kinds of inflation, or are there specific kinds that they're hard to get? And it very early on seemed to become clear that it was difficult to get. The various things amongst the things you predict in inflationary models are the spectrum of fluctuations that are measured, but you also predict that there should be gravitational waves from the early universe, and the amplitude of those waves and their spectrum is also something you get to predict. And all of the examples that had been found seem to have very low, they seem to be predicting unobservably large gravitational wave amplitude. And so a quick question became, is that something which is really generic to string theory, or is it just because the first few things you looked at were like that? And I think that that's probably still an open question, that there's some things that seem hard to get in string theory, some things that are easier to get. And I think there's a group of people that think about those still as to how you do that, less than there were in the 2000s, because I think it's a lot of the ideas have been explored already. My personal opinion is that there's two classes of things that generically come out at low energies in those models, and one of the things that drives all of these the thinking in these areas is, if you have these are scalar fields in the end of the day from the four-dimensional point of view. If you have scalar fields that are very light, that's actually when you have quantum effects, that's actually a very difficult thing to arrange. If you take a generic system and you ask, does it have a scalar field that's very light? Most systems don't. And the exceptions to that statement are cases where you have a Goldstone boson, or some sort of a symmetry reason why there's a very light degree of freedom. And the light degree of freedom is essentially telling you there was a symmetry in the full theory that you didn't know about, because it was broken. And so it involved particles you hadn't seen yet, or had fields you haven't seen yet. But there's two classes of Goldstone bosons in practice. There's there's what you would call compact Goldstone bosons, which are the traditional ones we think about, where they're like the axion, the things where the scalar potential is a trigonometric function. And those have been very well explored. And so since the late 80s, people have been thinking about those as being that's the traditional Goldstone boson. But there's a different class of Goldstone bosons, which are dilatons, which are coming from non-compact symmetries like scale invariance. And those are less well explored. And my take on what we know about inflation is that it's saying the data we have now can distinguish between those two classes of Goldstone bosons. And the traditional ones, the trigonometric ones, they can provide inflationary models, but they're hard to get in string theory for various reasons. And they don't describe the data very well. But the Goldstone bosons that come from scale invariance are easy to get from string theory, because almost every field, there's a lot of scale invariances in string theory, it turns out, accidental scale invariances. But not only that, they're a great description of the data. Those are the best descriptions of the data. The ones, the models that you hear about often, Higgs inflation or Starobinsky's inflation or alpha attractors, those are all essentially special cases of the exponential potentials that are the ones that you get from scale invariance. Trigonometric potentials are the ones you get from axions, which are really exponentials of imaginary arguments. And so exponentials of real arguments are what you get when you have non-compact symmetries. And I think that's really the message of inflation, is that you're seeing Goldstone bosons for accidental scale invariance. And that's something which is very easy for string theory to give you.
Okay. So would you say that this is a hint in favor of string theory at this point?
A very weak one. In the sense that I think in the end of the day, all the measurements we're doing are low enough energies that you can describe everything in terms of field theory. And so there's not any smoking guns there, but it's true that it's suggestive that the ingredients that you need are there. It's every single string vacuum that anybody's ever found, they all have these accidental scale invariances. That's one of the things that, and it's probably also true that the scale invariances have not been exploited very systematically, I think. So one of the directions of research, like a different direction of research I have, is to ask more generally, what can those scale invariances do at low energies for us? Can they help us solve other problems that we have? And I think right now the answer is we don't know, but it's again, it's not very often that you have an angle on how to think about low energy gravity problems, which is a new one that hasn't been thought through in great detail before, because these scale invariances have not been exploited as systematically as some of the other tools.
Okay, yeah, that's very quite interesting. And also, you mentioned axions, which are often referred to as one of the candidates for dark matter, right?
Right.
So still we are in cosmology at this point. So do you have any thought about, for example, aspects such as dark energy and dark matter and, what is called the dark sector of cosmology?
I have speculations.
Okay.
And I think the dark matter, I have very little probably to add that other people couldn't have said with more expertise. I don't know what it is. But I think the usual thing, the first thing everybody always thinks about is, well, if you have two things like dark energy and dark matter, wouldn't you really rather have just one thing, like modify gravity, and not have two things? Because we're inferring its existence from gravity, and if we were doing that wrong, we wouldn't need two things, and maybe that would be simpler. And like everybody else, I went down that road too, and I think probably it's fair to say that it's a nice thought, but it doesn't work. Or no one's been able to make it work. So I think it's probably the best right now. If you had to say what's the most likely alternative, I would say it's some sort of particulate dark matter, and it might be a axion like a field. It might be some heavier particle, and I really don't know what. But I think I have a better handle on the dark energy, which is normally the thing that people's attitudes to dark energy, as you know, people think that it's either very easy to have theories or it's very hard to have theories, depending on whether you worry about the cosmological constant problem.
Right. Yes.
And I think that's a fair observation. I think it's true that there are many models, many cosmological models that can describe the dark energy, and the cosmological constant is the best one, in the sense that it describes the data perfectly well. But it's a model in the sense that it's not really the thing. If you kind of ask, can I embed that model into a theory of higher energies that includes all the other physics that I know, should I expect to have seen that at very low energies? And cosmology is the lowest energies that we have access to. And what's the opportunity in cosmology right now is that many things in cosmology seem to require the use of very light scalar fields or a cosmological constant. So something which is a very small vacuum, a very small potential energy, or possibly if you're doing inflation, for example, a very light thing that's moving.
Mm-hmm.
And if you thought that the dark energy was time evolving, it would be, again, a very light, both a very low vacuum energy, a very low potential energy, and a very shallow one, because it's not moving very fast, according to the evidence of what we see. And the opportunity there is that if success of explaining the experiments is relying on something which is rare at low energies, then that's actually a good thing, because it means that there won't be that many theories that'll get it right. And although cosmological observations will not be able to distinguish by themselves amongst the various models that are around there, the extra information that it had to come from a sensible theory of the rest of the world, if that's a restrictive condition, that should actually be very useful. That's an important clue. And that's what the cosmological constant problem, that's the way I think about the cosmological constant problem. It's a clue. The difficulty of getting very small vacuum energy, very small potential energies and very small, very light scalar masses is an important, that's nature telling us something, that we're seeing something which is not generic at low energies.
Right.
And I think it's fair to say that the reason, I think everybody would agree that that would be a great clue if you could use it, but then the problem is nobody's found a successful way to use it.
Mm-hmm.
And because of that, I think many people have given up on the clue, but I think that they haven't looked hard enough yet. So I think that I think these scale invariances that I was alluding to provide ways to think about, ways to get smaller potential energies than you normally expect to get. Whether or not that's going to work in the end, I don't know, but I think that there's a direction of thought that hasn't been explored to the end that exploits that clue, and I'm still optimistic that it will get there. And it happens that you're led in these kind of the models that I'm thinking about that have scale invariances. My main opinion on dark sector that is probably not widely held is I'm kind of taking the point of view that let's say if the important clue is what we're seeing is hard to see from high energies, then let's ask, what does high energies want to give us? Given the observation that we are seeing light degrees of freedom, and that says that we should be looking for some sort of a Goldstone boson, and I think scale invariance is the one that hasn't been as explored as axions. But if you look kind of in string vacua, if you arrange for things to be light, what kinds of things do you get? There's two very generic things that happen, neither of which has been explored very systematically yet. And so the part of my research is trying to explore it. And one of them I kind of talked about already is the scale invariance. And so there should be Goldstone bosons for that. It happens that when you get Goldstone bosons for scale invariance, you often also get axions, because in string theory, they come as in a supersymmetric way. Mm-hmm. And the axion and the scale and the dilaton come as pairs in supersymmetry. So it wouldn't surprise me at all to find that there are axions, there's lots of axions that are around that could play the role of dark matter. Mm-hmm. I think that's an observation many people have made. But I think that the one objection to that is, well, we know that the world is not supersymmetric. Mm-hmm. So why should it be? We already know that that's true at the energies we can see in accelerators. Why should it be true at much lower energies?
Yeah, exactly.
And so the second generic thing that happens in string theory, which I think is underappreciated, is that what happens in supersymmetric theories is that you have particles, bosons, and fermions that are related by the symmetry. And if the symmetry was exact, they'd have the same mass. And so when you break the symmetry, they have different masses. But there's a pattern to how the mass splittings arise. And the pattern is that typically there's some field that breaks, whose expectation value breaks supersymmetry, let's say. Then the size of the splitting of any particular supermultiplet is proportional to that field that breaks supersymmetry, but it's also proportional to the strength with which the particle of interest couples to that field. Mm-hmm. So you tend to get hierarchies of splittings, and the more strongly you're coupled to the whatever breaks supersymmetry, the bigger your splitting is, and the less strongly you couple, the smaller your splitting is. So that's something which I think everybody would agree with. But now the observation is that the weakest interaction that we have in the problem is gravity. So you should be expecting that gravity very generically is the thing that's split by the least. Mm-hmm. And so it's not at all unusual to have, say, the graviton and the gravitino be split by much less than, say, the Higgs boson and the Higgsino. for example, if you're making models. But now imagine that it was true that the splitting in the particle physics sector is bigger than the energies we have access to. So all we see is the standard model. It doesn't mean that the splitting in the gravity sector is also that big. It could very well be that the gravity sector is split by less than that. It's actually very plausible that it could be split by less than that. And so that suggests a world in which there's a dark sector, the gravity sector, but there's a lot of symmetry in the dark sector, because the dark sector is gravity and all the things that are brought with it by supersymmetry.
Mm-hmm.
And that would be true even if the particle physics sector that we've tested isn't supersymmetric. And that's kind of a thought that people actually had in the 80s already. But what's made it into a useful thought now is people now know how to be systematic and to calculate with theories like that. So how do I describe a low energy world where gravity is supersymmetric and particle physics is not?
Mm-hmm.
And that turns out that's a solved problem as of 2010 or something.
Okay.
and it turns out that what you do is you can take any theory that's not supersymmetric, it just has bosons, let's say, but you can make it supersymmetric by coupling it to a Goldstone fermion in the appropriate way. And then now it's got a global supersymmetry, and then you can couple that to gravity, supergravity, the way that you always do. And so what really was required was a good understanding of the theory of the Goldstone fermion. And so you can actually flesh out now what that low energy world would look like. And so one of the programs I'm on is trying to explore that thought together with the scale invariance to see what it says about the dark sector. And I think it's early days, so it's not clear that it says specific things yet, but it means that there could be structure in the dark sector, and there's many candidates that could be there to play the role of dark matter. I don't know which one it is, but I'm kind of focusing on the dark energy because that's the harder one to get. And
Right.
so unsuccessfully, I think, so far, but I think we're doing better than anybody else has.
Okay.
is the fair way to say it.
Okay. Yeah. Yeah. Okay. That's very nice. And again, here we see another instance of how you can play with low energy systems, and well, cosmology is the stereotype of that, right? So it's as
Yes.
you said, actually, it's the lowest energy system that we know of, but
Yes.
with some information coming from some high energy theory model that we have.
Yes.
Another one that I may suggest for our chat here is that you also worked on a duality between ADS-CFT, the ADS-CFT correspondence, which is usually applied in string theory. Sorry, it's related with string theory, and quantum Hall effects, which again applies to solid state, right? So condensed matter.
Yes.
So can you tell us a little bit about that?
Yeah, that was a surprise. It was kind of a direction I did not expect to go, because I don't know, I'm not an expert in condensed matter physics, but I certainly learned a lot about it in the process of doing it. And so the I'm not sure how sophisticated your listeners are for ADS-CFT, but there's basically one of the surprises that has come out of string theory. I think it's, regardless of whether or not string theory is the theory of quantum gravity, string theory has taught us something already, something very useful, and that is that the space of quantum field theories is smaller than we thought it was, in the sense that there are two different quantum field theories which we used to think were completely different from one another, but we now know are exactly the same theory. And you might say, well, so how could you have been so stupid not to know they're the same? and what happens is, in these examples, they each have a coupling constant. And we typically only really understand the predictions of a quantum field theory in the limit when the coupling constant is weak. And it turns out that the connection between these two theories is, when you map this theory onto this theory, the coupling constant on theory A, let's say, is 1 over the coupling constant on theory B. So they're never both in the weak coupling regime. And that's kind of why we missed it. But what happened in string theory was there were various supersymmetric examples where you could actually understand the strong coupling limit, and then you could see that they were the same thing. And it's one of these really, this is the most remarkable thing that's happened in theoretical physics, I think, in my lifetime, which has been a long one, is this observation that there are these field theories that look very different, that are the same theory, and what's part of what's amazing about it is the dimensions of space that these theories live in is different. So that in the classic example, there's a 10-dimensional theory where it's compactified down to 4 dimensions, let's say, but or it might be compactified down to some other dimension. But what happens is that the one that's equivalent to it has one less dimension.
Mm-hmm.
And it happens that the one, so there's a state, so if you have a d-dimensional theory in anti-de Sitter spacetime, that's the ADS of the ADS-CFT, then it turns out that if the radial direction in the anti-de Sitter space, if you get rid of it and you just think of it, the anti-de Sitter space has a boundary. If you think of the boundary, which has one less space dimension, then there's a conformally invariant theory on that boundary, which is exactly equivalent to the theory in anti-de Sitter space, which includes the interior, and the connection between them, changing the radius of the if you kind of move the boundary in along the radius in anti-de Sitter space, that corresponds to changes of scale in the dual, the equivalent theory. So that kind of observation that these things are related is probably very deep. It probably tells us something about the emergence of space-time, and none of those things is what I was involved in. So I got involved in that because I was interested in quantum. Quantum Hall effect is kind of an amazing system. It's you apply a magnetic field, and then all the particles, charged particles, and it's systems that tend to be trapped in 2 space dimensions. So so you can do that in condensed matter physics by interfaces between two systems, for example, might be 2-dimensional, and so there's some sort of potential barrier that keeps electrons on a surface. You apply a magnetic field perpendicular to the surface, and then you have a bunch of Landau levels, and it turns out that that's a quantum system that's very degenerate. So the Landau levels all have the same energy at a macroscopic level. So there's a one Landau level. The degeneracy of that level can be proportional to the number of particles, the density of particles in your system. So it could be an Avogadro's number or something like that. It's a huge number. And a quantum system that is very degenerate, there's many things, in many ways in which you can be surprised by interactions. They don't have to stay weak because there's the energy cost of mixing with other states is 0 essentially. And so they found all these remarkable effects, which include fractional charge and fractional statistics of quasi-particles and all kinds of crazy things. But one of the craziest things was that there's many quantum Hall vacua, and they're all labeled by various quantum numbers. And it seems like they're labeled essentially by you have an ohmic resistance, and then you have a Hall resistance. So you apply a electric field, you have a plane, so X and Y plane, you apply an electric field in the X direction. Normally you get a current in the X direction, and the proportionality of those 2 things would be the ohmic resistance. Mm-hmm. But it happens with a magnetic field, you also get a current in the transverse direction too, because the things are moving in these Lorentz orbits. Right. And the Hall conductivity would be the proportionality of the current perpendicular to the field you applied it. And it turns out one of the remarkable things is that conductivity is quantized in units of E squared over H, and it's a perfect fraction. It's always, and typically in most systems it's a fraction where the denominator is odd, and the accuracy of the measurement that's a fraction is it could be 10 decimal places in the measurement, but it's as accurate as you can measure it. And now it's used as a standard for measuring the fine structure constant. It's so accurate. So it's phenomenally accurate. And so those kind of things are really, really remarkable. And it turns out one of the things that was that I kind of, what started me off thinking about these systems was they have lots of properties. As you change the magnetic field, the fraction changes. And so there's lots of transitions you can look at. And it turns out there's something that they call super universality, that it turned out that all the various properties you would measure as you made a transition from one fraction to the other as you change the magnetic field, it didn't matter which pair of fractions you're looking at transitions between, it was always the same answer. Mm-hmm. So it was like they were all the same system, but there's a big symmetry that mapped all these different vacua to one another, which had these different fractions. And somebody made the observation that that a group that would do what you needed was one of these groups that appears in string theory. So it was one of these modular groups, SL2Z. And so someone just made that observation. There's really no reason why it should be relevant. But then as we started thinking about it more, you could see that that there's a kind of a special case of duality in 2 dimensions where a particle which has a charge in 2 dimensions, has the same description as a vortex. If you had a field which had a vortex perpendicular to this 2-dimensional plane, it looks like a particle essentially. And there's a very precise way in which the particles and the vortices have very similar dynamics. And so if your conduction electrons were replaced by vortices, it turns out that you could understand why the symmetry, there could be a symmetry that would relate all the various kinds of fractions. And that observation was kind of an interesting observation that had been made in the early 90s, late 80s, but then it just kind of sat there because there was really no known theory of electrons which had that symmetry in it, or any theory of interacting charges that it was an example that exhibited that symmetry. So it was very difficult to know how to do anything with it. So then what happened was I stopped thinking about it. But in the meantime, people like Ed Witten kind of made the realization that that this particle vortex duality was actually very general, that if you had a 2-dimensional system, it very, very generally wanted to have this kind of a symmetry. It wasn't clear why electrons would show up that way. Mm-hmm. And then the final thing that happened was what made me think about the connection to ADS-CFT was people were starting to, they since at some point they discovered ADS-CFT and they were exploring its applications, and they started to ask, can you describe systems like condensed matter systems in this way? Can you have new interacting, since the basic idea of ADS-CFT says there's 2 theories that are the same, one of which is weakly coupled, one of which is strongly coupled. Can we make models of strongly coupled systems that we can now explore and make predictions for, because we now know in secret that they're weakly coupled if we think about them right, and we can calculate everything. But then we can ask, does that look like anything we see in these strongly coupled condensed matter systems? And so there was an effort made to try and, it was kind of like throwing darts at a dartboard, that, can you find anything that looks like something that has been seen experimentally? Mm-hmm. And I remember thinking at the time that what you need to guide that process is a symmetry, and the quantum Hall systems have this great symmetry. So if you could ever find any kind of quantum Hall system that had that symmetry, any ADS-CFT system that had that symmetry, then you now have a better handle on the kind of strongly interacting physics you're looking at, because it'll for free have all these things that are the experimental consequences of the symmetry. And so then it turns out that right before we wrote our papers, somebody worked out basically the symmetries. If you have an electromagnetic, if you wanted to describe a quantum Hall system in this dual language, the duality, you have to have an electric charge, because these things are conductors. And if you kind of and it also, it's always true that when you take the conformal field theory and turn it into an anti-de Sitter space, gravity is always there. So you have to have at least electromagnetism and gravity. And so somebody made the observation that that led us to think that as soon as you have electromagnetism and gravity, electromagnetism has a duality symmetry, which is magnetic monopoles being interchanged with magnetic charges. So there's an automatic duality that we know happens there. And it turns out in 2 + 1 dimensions, there's another symmetry which is also there, and that is you can always take a boson and turn it into a fermion in 2 dimensions just by adding a flux tube to it. Mm-hmm. And so those are kind of 2 kind of discrete transformations where I can take a boson to a fermion, I can then make it back into a boson. So it seems like it's just a very simple symmetry. And magnetic electric duality is another simple symmetry, but it turns out the interesting thing is that they don't commute. Mm-hmm. And so when you do them one after the other, you generate a very big discrete group, and it turns out it's this group that you need for the quantum Hall system. Okay. So that was the observation, is that the quantum Hall system, the ADS-CFT system, when you have electromagnetism and gravity in anti-de Sitter space, it likes to have the symmetry which quantum Hall systems seem to have. And so it also likes to describe what is a strongly coupled system. So now that opens up the possibility that you might be able to make good models of strongly coupled systems with these symmetries, which seem to be present in the quantum Hall systems, and for which it was difficult to do anything before because you didn't have a concrete example which had those symmetries. And so it was kind of interesting to find that. And I still think that 20 years from now, when they talk about quantum Hall models, they're going to ultimately take them from ADS-CFT, but it hasn't happened yet. And I think the reason it hasn't happened yet is the missing ingredient is in quantum Hall systems, they have disorder. And disorder is something which is an important part of what you're looking at when you measure the various observables they look at rely on disorder. And what's missing on the ADS-CFT side is a description of disorder. I think if you had that, then you probably would have what you need to have a nice description of a strongly interacting quantum Hall system with dualities manifest. But I kind of I've been a tourist in that because I'm not really a condensed matter physicist. I'm not really a string theorist. And it was just an opportune connection that I could make.
Right, right. Yeah, and actually, I mean, in the entire conversation that we are having, so I'm noticing two big trends, which I find very fascinating. The fact that you were able to connect areas of physics that usually are perceived as completely different, right? So high energy physics, so in this case, string theory, or quantum gravity in general, and condensed matter, which is usually considered as low energy. I mean, we are so in condensed matter and solid state, usually we deal with stuff that we can make in a lab or something like this. Quantum gravity is famous for not being, we are not able to make quantum gravity in a lab, at least not yet, hopefully in the future.
Yeah.
Another interesting thing that I'm noticing is that, and you mentioned this several times, is that at some point you had the impression that a new topic would become interesting, and so you decided to study that topic and to get some knowledge so that you could ask interesting questions in that topic. I found this very interesting and very encouraging, for future generations, because sometimes changing topics can be very scary sometimes, right? So because
yes,
you're
very much so. Yes,
comfortable in your topic, and someone telling you, well, you should look these other things, and you feel your seat shaking a little bit. So I found this very, very interesting. But there is one question that I was planning to ask you at the beginning, but then I forgot. So why do you think we need quantum gravity at all at this point?
I don't have a deep answer for that. Before you leave the thing about changing fields, I think the thing that allowed me to change fields was job security. As a postdoc, if you're trying to get a job, it's very difficult to make that transition. But that's one of the great things about tenure is that you can take the leap like that, and my experience it's been good. So people debate about quantum gravity. Why do you have to quantize it? And I think my attitude towards that is that there's lots of evidence that the world is quantum, and there's lots of evidence that general relativity works. And so then the radical point of view is that you have to give up one of those two things. So I think for me the thing that is more likely to be fruitful is, if it's difficult to make those things work together, but not impossible, which it seems to be, then we should push that and see that's a very, very tight framework, and that's going to make specific predictions of what we can test. We can make it. We can at least make the predictions, and maybe you can test them, maybe you can't. But it sounds like we should explore where that takes us, because the alternative is we say, well, so either things are not, gravity is not quantum, then we need to invent a framework where we know how to control the errors of everything. Right. And I think that that's not to say that it can't be done, and it's but it means that the bar is very high, in the sense that and for me, I would be kind of more inclined to go that direction if people had already explored very systematically the simplest thing, where things are quantum mechanical and gravity is general relativity. But it turns out that hasn't been explored very much at all. I think it only seriously started to be explored in the 90s, when John Donahue actually did some calculations of what the quantum corrections were in gravity. And although Weinberg had made the point in the 70s that it can be done, he didn't do it. And so now by actually doing the calculations, that you can kind of see precisely what the effects are and what the surprises are. And I think we're still in the stage where very few people are actually making explicit calculations, even at the one loop level in gravity. And if you think about any other theory that we believe to be true, if you ask, is there a simple quantum calculation I could have done? The answer is there are lots of simple calculations, but Pauli did them all in 1930. Gravity is the exception. And so I think for me, since we're looking for clues as to what to do next, I think part of my program is I'd like to do as many explicit quantum calculations at the one loop level involving gravity as possible, because that's a theory we think is actually right. and so those loop corrections are eventually going to be important. And we can't measure them now. I'm happy to be the Zeldovich of tomorrow, do something that is tested much later. but almost certainly you're going to learn something interesting by doing explicit calculations in the framework that we have. And I'm glad that smart people think about the alternatives, but my money is that that's actually the more likely way along in this case, the conservative point of view, I think is more likely to be the fruitful point of view, I think.
Okay. Yeah. That's well, my money will be on that as well. But again, so it's a bet. So we don't have anything on the table right now. So
people vote with their feet, right?
right. Yes. Thanks a lot. I mean, this conversation was great. So I have one last question. So what would you say to a student, master or late bachelor, that is trying to decide what to do with his career? So what would you suggest him or her about what to think and what to look out, and so how to approach the future of his her career?
That's a good question, and probably the best advice I could give is to be more thoughtful about it than I was. Yeah, I think in my day, you didn't have the internet, so it was much more. People I think fell into careers in a way that probably is less common now. What I admire about young people now is that they often are very thoughtful about what their choices are, and there's lots of resources they can. If you decide you want to be working on quantum gravity and you want to be an academic, you can look at all the places that do that. Where did those people get hired? And so what's the path that gets me there? And you can research it because it's all on the internet basically. And it seems to me that young people are much more savvy that way already than I was. And they should definitely do that and keep doing that, because I think that's be thoughtful about what you want, and inform yourself as to how to get there, and be proactive, have agency. And it doesn't necessarily mean that it has to be in academics. I'm very happy in academics. It's a great life. But in the end of the day, universities are not growing. So on average, every professor gets to replace themselves once, and everybody else is going to do something else. Right. And the good thing about a physics degree is that you can do so many things with those tools. And so I know many people, I probably know more people that are not academics than are academics who had been in academics before. And for some of them, they feel it's a failure, and that's actually a blight on their life. But most of them, they're doing interesting problems, and they're doing, it's not the ones they thought they were going to be doing, but they have very, very good lifestyle, thinking about interesting things, and they're paid 5 times as much as the academics are. So I would say, think about what you want in lifestyle, what you want to think about, and pursue it. And if you're going to stay in academics, work on what you like, because the people you're competing with are spending as much time as they can on it. And the only way you'll do that is if you like it. So right. Do what you like.
Right. Awesome. Yeah, thanks. Great suggestion. And I think we hit the 1 hour mark. So I think it was a great conversation. There were many interesting topics and many interesting, considerations on several aspects. So I would like to really thank you for first of all, having accepted the interview and having, the interview with me. And it was a great pleasure having you. So,
well, as they say, it takes 2 to tango, and I thank you for the thoughtful questions and for the invitation in the first place. I enjoyed it very much. Thank you very much.
It was great. Thank you.